It is my immense pleasure to open this seminar series with my talk, and I hope that my talk stays up to your expectation, guys. But first thing first, to tune the level of the presentation, I want to ask you, how many of you are familiar with the network? Does everyone know what the network is? Can you raise your hands if you are familiar? Good. Are you familiar with what the network embedding is? You could raise your hand if you know what the network embedding is. Okay, so roughly 50%. Okay, I'll try to then steer my presentation more to lower level things rather than high level things. But anyways, I'm gonna start with some basic propaganda. This is the very first talk, and of course, I know some of you guys, but in no way I know everyone here. So I'd like to say a few words about where I'm coming from. I'm coming from the high-rise building. This one. Okay. And I'm coming from the network architecture and services section. And generally, we are a team of experts in networks. We started with telecommunication networks, but we gradually expanded our interest to pretty much all problems that are related to networks. So we are interested in networks broadly defined. If you have a network of interest and you want to talk to us, you'll have our attention. This is our group at glance. We have about 6 staff members, 3 senior researchers, about 10 PhD students, all working on different problems on network sciences. Some lines of research that we are pursuing actively that I'd like to mention are epidemics and networks. I don't have to explain to you guys why it's important to study epidemics. I hope. We are interested in net robustness of networks. We know that our networks operate under real-world conditions. There are adverse events, there are failures. We want to understand to what extent networks are able to withstand different types of damages and retain their functionality. We are interested in control of networks. Given the parameters, we want to understand to what extent we can drive the networks to different states and how to do this. We are interested in telecommunication networks. There is a particular emphasis on next generation of wireless networks. We have a number of professors working on these questions. So if you are a master's student looking for a project, or if you're a PhD student looking for a PhD position, and you are interested in working on one of these topics, please come to see us. We'll be very happy to talk to you. If you have a problem related to these topics, also please come to see us. We'll be happy to talk to you and possibly collaborate with you on these problems. Well, I keep on forgetting that there is one more research line about network geometry that I'm interested in, and I will talk more about network geometry research line right now. So, when I talk about network geometry, I think of network embeddings. What is a network embedding? In most general case, well, there are network node embeddings, there are network link embeddings. I'm always thinking about network node embeddings. I'm thinking about a procedure of mapping network nodes, this is a network, to points in certain underlying space, such that the nodes have coordinates in the space, and I can use the geometry in the space to solve certain problem of interest. So there are many different approaches to do network embeddings. There are also many different ways to represent networks in the spaces. One important thing that is common, however, is how we think about network embedding. We can think about distances between the nodes reflecting certain measure of how similar they are. That is, if we have a network embedding, we want to have similar nodes being close to each other and dissimilar nodes being far away from each other. Why is that? This idea comes probably from social networks, where it is the similarity is recognized as an important factor. If we are similar, all other factors being equal, we have higher chances to do it. So I use this point representation for network embeddings. Many of you might be more familiar with the vector representation, where instead of having a point in the space, you learn a vector per node or several vectors per node maybe. And then the similarity is defined not by the distance, but by the inner product of two vectors. The more closer they are to each other, we assume that they are more similar and more likely are to be connected and maybe more likely to share the same properties. Most of my talk is going to be on the high level, and most of the things I'm going to say about the point representation will probably you'll be able to convert into the vector representation as well. So, but since I'm more eager to work with point representations, I will use that for my talk. So let us move on. So it is the similarity interpretation that lies in the heart of network embeddings. If you have a different opinion, please let me know, and I'll be happy to talk about that as well. And because of the similarity interpretation, similarity seems to lie in many different applications of network embeddings. One umbrella of such applications is network reconstruction. If your network is incomplete, to identify missing pieces, you might want to embed your incomplete network into the space and then look at distances, use distances and geometric vicinities to reconstruct your network. For instance, if this is your network embedding, you see that two nodes are close to each other, but they don't have a connection. You might think that they're similar, and maybe it's the case that they are having a missing link. Conversely, if there are two nodes that are far away from each other, you might want to think again of whether or not they have that link. Maybe it's a false positive link and they shouldn't have a link in the first place. Another umbrella of application comes from the classification, which also has its roots in similarity interpretation. Imagine you know some properties of nodes in the network, but not all of them. So you want to infer some properties of the nodes you are interested in. Here, the properties are encoded with colors. So imagine you want to know the color of this guy, but you know the color of its neighbors in the embedding space. The basic idea is you might want to look at the neighbors of this guy, and maybe you want to conclude that it's more likely to be yellow than it is likely to be green. So it's a very basic idea. How exactly you do classification, there are many different ways to do it. These are the most intuitive applications. There's many more, and just to mention a few, there are applications to search, where you can search for certain information in the embedding. There are applications to routing, which is of particular interest to our group. In the end of the day, if you want to send information from one node to another node in the network, you might, instead of using the topology of the network, use the geometric coordinates of nodes and do the routing based on these coordinates. And last but not least, I'd like to mention one of my most recent works. It turns out that if your network representation is good enough, you can also find shortest paths. Well, if you have the network, complete network, you don't want to use network embeddings to find shortest paths. You might want to use just the standard graph theoretic methods like the extra algorithm. But what if you have 50% of the links missing? The extra will probably give you some wrong results. But in these situations, you can still use network embeddings, and you can use geodesic curves in the space in order to be able to find where shortest paths lie and use that to identify shortest path nodes. Well, if you invite me for another talk, I will talk about that. But today I'd like to give a more general talk on a slightly different concept. So we know why we are doing network embeddings. If you think about network embeddings, there are so many different methods that I'm afraid that I only know a very small fraction of them. This is a very recent paper on the review of different network embedding methods. There are many different reviews. Here is the taxonomy that the authors came up with. So loosely speaking, according to this taxonomy, we can split network embedding methods into two large categories. what the authors call deep learning-based methods, which are machine learning methods that you use to obtain network embeddings, and also what they call, it's not my words, they call shallow methods, which don't use machine learning methods here, but use nevertheless some sophisticated mathematical techniques, such as matrix factorization methods, random walk-based methods, optimization-based methods, and etc. There is a merging slice of a pie over here coming from higher order networks, where we talk about simplicial complexes, hypergraphs, etc. And most of these methods, they routinely assume that your space to which you're embedding is Euclidean space, which may be a good thing if you think about simplicity, but may not necessarily be the most optimal for your network embedding. So what I'm interested in, which according to this review is classified as an emergent method, in hyperbolic network embeddings. And here, instead of using Euclidean space, I want to use a hyperbolic space. What is a hyperbolic space? Basically, it's a space with constant negative curvature. I can talk for a long time about what the geometry is or what this curvature means, but for the sake of concepts, let us just define some basic properties. So if you're a mathematician, you're interested in rigorous definition. A two-dimensional hyperbolic space can be defined as a surface of a hyperboloid that lives in a Minkowski space-time of +1 dimension. If you're heard of hyperbolic spaces, you probably have heard of Poincare model. You can relate hyperboloid model to Poincare model by projections through a point of 0, 0, -1. But if you want to abstract away from geometry, what you want to remember is we embed network nodes not into Euclidean space, but onto the surface of this hyperboloid. Points are placed here. So why, in the end of the day, you might want to consider hyperbolic spaces as embedding spaces? Again, at a very high level, let us compare a Euclidean disk, two-dimensional Euclidean disk, to hyperbolic disk. What do we know about the two? First is the volume. Euclidean disk, two dimensions volume is the same thing as the area of the circle. That's pi r squared. It's proportional to the radius squared. If you have a higher dimensional Euclidean object, it becomes a ball. What is the volume of the ball? It's proportional to the r to the power of d. So the volume of Euclidean spaces grows polynomial. How about hyperbolic spaces? The volume grows as proportional to the hyperbolic cosine of radius r, which for large enough r is exponential growth. So that's one immediate difference that we see here. Even at 2 dimensions, hyperbolic disk grows exponentially, which can be we can say is loosely equivalent to infinitely dimensional Euclidean space. So this exponential growth of the volume has important implications for geodesics, or shortest path curves. We all know from elementary school that the shortest path in Euclidean space in our physical universe is the straight line, this one, from A to B. In hyperbolic disk, this is not the case, and you can easily understand why. Because the amount of volume at the periphery of the disk is exponentially large, it's going exponentially compared to the volume in the middle. So it's very expensive distance-wise if you want to go through this exponentially large volume from A to B. And instead, what you want to do, you want to walk towards the center, turn around somewhere, and then walk back to your destination. So geodesics in hyperbolic spaces, they are more curved towards the center of the space, Now, this is what we know about hyperbolic and Euclidean space. What do we know about networks, real networks? That one, does it ring the bell? What is this? D proportional to logarithm of n. Where is this coming from? This is related to the so-called small world phenomenon, or more commonly known as the 6 degrees of separation. There was a theory that I know anyone in the world by at most 6 handshakes. More mathematically sound formulation is that typically network-based distances in large networks tend to scale logarithmically with network size. So if my network grows by a factor of 10, the typical distances, the average distances, will only grow by small additive factor. So if we take d proportional to logarithm of n, we can think about n as related to the volume. It's an analogy of the volume for the network. We can assume that volume grows exponentially with distance in the network. If I count my neighbors of neighbors, neighbors, then neighbors of neighbors, then neighbors of neighbors of neighbors, they are at least in the local vicinity, this number will be growing exponentially with the number of distances. This much better agrees with the hyperbolic growth of the exponential growth of the hyperbolic space rather than Euclidean space. Well, it doesn't mean that we should throw away Euclidean or Euclidean embeddings, but what it implies that for Euclidean embeddings, you might want to use higher dimensional spaces, which is in fact being used. It's not uncommon to see 500, 1000 more dimensionality for the Euclidean embeddings. In hyperbolic space, you can get away with just 2 dimensions to start with, but you can use higher dimensions as well. Now, there is one more aspect about shortest paths. What do we know about shortest paths in real networks? They tend to go through the center of the network. And here by center, I'm loosely speaking about hubs, large degree nodes. So again, this notion of the shortest path going through the center of node somewhat better agrees with the notion of the geodesic, which is a continuous version of the shortest path in the space, which also goes to the center. So somehow intuitively we see that hyperbolic spaces are more aligned with large-scale structure, hierarchical structure of large networks. That's why it's fascinating for me to explore how we can use hyperbolic spaces for network embedding tasks. Now, this is not specific to hyperbolic spaces, but if you are working with network embeddings, to a certain extent, you can get obsessed with network embeddings and think that you can apply it just to any network out there. Well, if this is really the case, is every network embeddable? The clear answer is no, not at all. And you can easily come up with examples of non-geometric networks. This basic example that everyone should be familiar with is the GNP network model or Ehrlich-Schwenning network model, where any pair of nodes is connected with the same probability equal to P. This is a clearly non-geometric network. You can think about many network models which don't have geometry at all. And you can think about many real networks which are more like GNP rather than some spatial network model. So you shouldn't be blindly use embedding methods for just any network. You want to think about whether your network is geometric. So this question invites a lot of open and very hard problems. One such problem is assessing if your network is embeddable in the first place. It's tempting to say, okay, I'll have my application, I will do embedding, and then I will think whether the network is, if the application works well, then I don't have to justify whether or not the network is geometric. But nevertheless, this is a very important fundamental graph theoretical question. Given the network, without doing any embedding, can you assess to what extent it's geometric? So we don't have the answer to this question yet. There are some initial works. There are some works I'm aware of. There might be some other ones. So one way to assess it, one work suggested clustering, or the density of triangles in a network might indicate that network is geometric. Why there are geometric networks? There are a lot of clustering, a lot of triangles, because of the triangle inequality that constrains the distances between triplets of nodes. Related, open, and very hard set of questions here is about what are the properties of your latent space that you want to use for the embedding. Should you use Euclidean space or hyperbolic space or maybe spherical space with positive curvature? What is the right dimensionality? What is the right volume of the space? Of course, you can learn the space as well by doing network embedding, but the questions are, can you say something about the embedding space before you start any machine learning or network embedding procedure in more general case? So here I'd like to mention some of the works by my colleagues, showing that there is one notion of discrete curvature that you can estimate from the network itself. It's called Olivier curvature. And there is a recent proof by Pim van der Hoorn from TU Eindhoven saying that in large graph limit, this Olivier Ricci discrete curvature converges to the continuous Ricci curvature of the space. There is another work I'd like to mention here about finding dimensionality of real networks. It's primarily for hyperbolic embeddings. You can use the density of triangles and quadrangles and higher order loops. And based on their behavior, you can understand what is the right dimensionality of the space that you might want to use as the hyperbolic embedding. So there are, in addition to practical questions, there are a lot of hard open problems in the mathematics of network geometric representations. Now, I don't work actively on these problems, but there are related questions that I'm interested in. And to steer your attention to these ones, I want to come back to the question, for a rather philosophical question. Why network embedding methods are so popular in network sciences, machine learning, data sciences, etc. So here is my understanding of this. You can probably have to trace it back to the similarity principle that says that birds of feather flock together, or similar nodes are more likely to be connected. The rise of both network and data sciences can be pinpointed to the early 2000s when our computing power became enough for us to collect and store large amounts of data. Before the data, we only had some graph theoretical models around 2000s where we were able to start collecting the networks. And historically, the first networks that were relatively easy to measure were social networks, maybe some World Wide Web data. And again, because similarity is a driving factor in social networks, this is one of possibly the reason why similarity became the dominant principle in network and data sciences. This is a historical reason. There is a mathematical reason as well. The similarity has a very important property, which is called transitivity. Imagine you have this toy network over here. If A is similar to B and B is similar to C, it is quite possible we expect that A is also similar to C to a certain extent. Now, you are embedding this toy network, and these nodes become points in your space. If A is similar to B, then you expect that your distance is small and A is close to B. If B is similar to C, this distance is also small. But if it's a nice space with a metric property, we have triangle inequality that says that distance from A to C cannot be larger than sum of the two. So DAC is also small, which invites such effects as triangle closure, and which agrees perfectly with transitivity of similarity. If you think about vectors, you could probably make the same argument. You have three vectors, which are at various, two pairs have very small angles, one and then third one, and then the third angle is probably also constrained by the other two. So this argument also works for vector representations as well. So it is the agreement between the transitivity of the similarity and triangle inequality of embedding spaces that invites our physics intuition. In the end of the day, we live in the three plus one maybe dimensional world, and everything we have experience with is comes from the physical world. So this invites all sorts of analogies that we take out from our physical world and apply to networks. That's why many of us think about network nodes as points. That's why we think about paths often in network as some trajectory in the space. That's why we think about communities of nodes as some dense regions of network nodes in some space closer to each other rather than to the rest of the network. So this intuition of similarity works perfectly as long as your network is driven by similarity principles. Is this really the case? Not in all networks. If you remember something about chemistry, you know something about covalent bonds. When atoms come together to create a covalent bond, they share some of electrons together to complete their orbitals. So here in the covalent interactions, the atoms, they share their electrons, so they complement each other orbitals by bringing enough electrons to them. So here we can already see that it's not based on similarity, but more based on complementing each other's property. Well, we are more interested in organic molecules like proteins. And there is a lot of evidence that proteins, which are complex structures, interact not because they are similar, although there is such an effect as well, but more if they complement each other with respect to their biochemical and physical properties. So there is evidence that in biological networks, molecular interaction networks, interactions are because of complementarity. Another example, interdisciplinary collaborations. If there is a hard problem that spans several disciplines, and I'm a network scientist, do I want to get another person as my collaborator who is very similar to me, or do I want to get someone from computer science or from biology to solve the problem? I would be much better off if the person has a complementary set of skills. So that's another place where we expect to see a lot of complementary effects. Business relationships. Do you think Apple trades with Huawei? Maybe. But they're more likely to trade with ASML that has something to offer to both of them, which is microchips. And then Apple and Huawei probably are competitors to each other because they have similar products. So complementarity has been shown to exist in business networks. And last example is text. Our language would be very boring if you were putting words in this of the similar meaning next to each other. Instead, to make it colorful and contrastful, we want to have words of all different meanings that complement each other nicely in some intricate way, creating some nice finished sentences. How exactly it's being done? It's an open question. ChatGPT probably knows how to do it, but it cannot teach us to do it efficiently. So it's important for us to understand what is going on in these sophisticated machine learning black boxes like ChatGPT to a certain extent. So a lot of networks that are complementarity based. Why should we be worried about them? Because complementarity is not transitive. If A complements B, B complements C, doesn't really imply that A complements C. What happens if you use an off-the-shelf network embedding method or just any network that is geometrically inspired? We again come up with this triangle inequality, suggesting that this distance is small, this distance is small, implying that A and C distances are also small. So if we use off-the-shelf similarity-based method with the complementarity data, it may lead to all sorts of inference problems. If you're talking about link prediction, it can tell you that A, C should be connected. Are they connected in complementarity network? Not likely, because A and C is not expected to be complementary. If you think about classification, because all distances are small, you might think that all A, B, and C are similar to each other. Are they similar? Not at all. A and B and C are complementary. Whether or not A is complementary or similar to C, we don't know. And in fact, I wish I was the author of this idea, but it came from a collaborator of mine who was shown that in the context of protein interaction networks, you cannot do link prediction based on common neighbors, because common neighbors is an analogy of a network embeddings. In social networks, if you have a lot of common neighbors, you're more likely to be friends. In protein interactions, it was shown by Istvan Kovac that this method doesn't work at all. It fails extremely badly. And instead, you want to use paths of length 3. So this was a eye-opening paper for me. I have my own blisters. They're already healed. But I've been working on network embeddings of biological networks for many years. And I was banging my head against the wall, asking, why can I not do anything pretty much in biological networks? So this realization that you cannot just take network embedding approach and blindly apply to a complementarity dominated network immediately asked me, can I still do something with network embeddings? And almost immediately I could come up with a quick fix for this. Here is the idea for the quick fix. I say that I no longer want to map my nodes to a single point. I might want to represent myself by at least 2 points, or maybe more points. And how should I think about them? It's my skills. If I'm collaborating, this is my knowledge of physics, this is my knowledge of computer science, there might be a little bit of chemistry somewhere. And then your knowledge is also represented by multiple points. So if I'm talking about complementarity, I want to relate my knowledge of physics to your knowledge of computer science. And the distance between them somehow should reflect such complementarity. Or alternatively, maybe my knowledge of computer science will complement your knowledge of physics. So quick fix solution for network embedding of complementarity network is to break away from the assumption that one node, 1 point. You want to use multiple points per node. And then relating the points of different type could probably quantify the complementarity. So this is the quick idea. You can see now, easily verified. I'm not going to do it, that now you have no problems with triangle inequality. You have no problems with quadrangles. If you do this network embedding, and you can apply it to many different network embeddings, you can just fix them with by providing more nodes per point. Here is one example to build our intuition. This is the network of antonyms, clearly non-similarity based network. 2 words are connected if they have opposite meaning. So here we use the minimal representation. So each node has 2 points. Look, for example, word free has green rectangle and green circle. If you zoom into the neighborhoods, what we see is now the neighborhood split based on the meanings of word free. Has at least 2 meanings. Free is cheap, and free is freedom. If you look at the upper neighborhood, you see that it's clearly related to the cost. The node free is close to the antonyms busy, costly, price, which are of different type, but it's also close to the nodes that are represented as circles, which quantifies the similarity between them. Free is close to receive, free is close to steal. Well, not exactly, but there you can see some analogy. On the other hand, free is close to antonyms such as free is close to antonyms of servant, of slave. So these are closely opposite meaning. And if you look at the same type points, it's close to free man, it's close to master, it's close to freedom. So using this complementarity embedding, and this is also a hyperbolic embedding of complementarity, you can find not only links which correspond to the antonyms, but you can also see do tasks as clustering by finding similar nodes. So this is a quick fix. You can see that it helps you to solve the problem. You can quantify how well you're doing by retreating back to link prediction tasks. You can see that with hyperbolic network embeddings, you can see substantially higher link prediction accuracy compared to similarity-based methods. If you talk about non-similarity-based methods, there are still some methods that are better than our method because it's probably a quick solution. But nevertheless, we can see that our method is also competitive with non-similarity-based methods. So we see that there is a lot of potential. Now the question is, what is the principal solution for complementarity representation? And to what extent you can use the quick fix for to solve the problems of interest? If you think deeper, there are many open questions. So if there are more skills per node, I'll put more points. How do I enumerate all the relationships between them? Not very easy to do it. Another more critical question is this: why do I put physics and computer science knowledge in the same space? They seem to be different objects, like apples and oranges. How can I compare apples and oranges? What does it even mean that I compare my knowledge of physics to your knowledge of computer science? Another question that you can ask is, why all of a sudden distance was similarity measure, then it becomes complementarity measure? How do I deal with this? So all these questions invite us to redevelop complementarity from the first principles. And what can be more basic as Oxford addiction, which says two people are complementary, but that complementary are different, but together form a useful, attractive combination of skills, qualities that allow you to solve something. So using this Oxford Dictionary as a starting point, you can say that, okay, we were right in the first place. We want to have different skills. Very good. And then we have each skill corresponding to a different point in the space. At minimum, we have to have two skills if you want to say how they complement each other. If you have only one, then it's similarity. So then what we do, we think about our skills, but we probably better to put them into different space. This could be physics domain of knowledge. This could be computer science space of knowledge. I have some knowledge in physics. I have some knowledge in computer science. You have also some knowledge of physics, some knowledge of computer science. And each of these spaces can be regarded as our conventional embedding spaces, which represent similarity. I can quantify how my knowledge of physics is close to your knowledge of physics and how my knowledge of computer science is close to your knowledge of computer science. But it's not straightforward to compare. Currently it's impossible to compare my knowledge of physics to your knowledge of computer science, which is the way it should be. How do we connect two spaces? Well, we wouldn't have to connect them if not for the scientific problems that we had to solve that span multiple disciplines. So here I'm assuming that there are interdisciplinary tasks that live simultaneously in both worlds. So mechanistically, I can think about my challenging interdisciplinary problem as having two disciplinary parts. The Pac-Man part belongs to the physics space, the droplet part belongs to the computer science space. And most basic mechanistic assumption I can make is that I solve the problem independently. If I solve physics part and you solve computer science part and we know each other, we have solved the problem together. So then we can say that the distances between you and the computer science part of the problem quantifies the chance of how more likely you're to solve that part of the problem. Distance from me to the physics part quantifies how likely I am to solve the physics part of the problem. Then you can start writing down some probabilities which you can use for network embeddings. You can say that one way to solve the problem I solve the physics part, you solve computer science part. Product of two probabilities that are dependent on distances. But in the real world, it's possible that you solve the physics part of the problem and I solve the computer science part of the problem. So there is another probability that is possible. So together, it doesn't matter who solves what part. In the end, we have the joint probability to solve this problem as a product, as a combination of two possibilities, the union of two probabilities. And then you can finally write the probability, the complementarity between us as the probability that you solve at least one task jointly. Here I'm assuming that all tasks are independent. Maybe not a good assumption for collaboration networks, but maybe a good assumption for biological networks, because different proteins may do some different functions, which are analogous of problems. So to summarize, this new principal complementarity frameworks has important connections to the minimal framework. The minimal framework that we used for the embeddings is a special case of this principal complementarity representation. And also complementarity contains similarity as a special case. We can prove that. There are open questions. One big question that maybe some of you guys can answer: to what extent this principal complementarity framework, where we have multiple spaces and tasks binding them together, to what extent it's even learnable in the first place? Can we learn all node coordinates and functions, connection probability functions, or is this going to be some ill-defined problem where you will have some degenerate solution? So that's an important open question. And another related question: can we simplify the framework? What are the acceptable classes of simplified versions of this framework that can be applied to different disciplines? So I'm hoping that to hear some ideas, criticism, and maybe to establish collaborations along these topics. And these are the network theoretic and machine learning questions. There are other implications that I'll probably skip that come back to the high-level picture. You have to rethink about how you think of paths, because in the complementarity networks, paths can be completely disjoint. You have to rethink about how you think about communities. In similarity, it's coherent structure sitting close to each other. What it is in complementarity representation, we don't know. It could be multiple clusters corresponding to the same community of nodes. So there are a lot of disciplinary problems. I don't have the time to spell all them out, but I'd like to stop here and invite your questions.